In section 3.5, we're going to look at another group of functions called rational functions. Up to now, we've looked at quadratic functions, polynomial functions, and now we're going to look at rational functions. And like the previous chapters, we're going to look at some topics individually and then really put them all together to graph the functions. The first thing we'll look at are the domains of rational functions, and this is really very similar to what we looked at in section 2.6 when we looked at the domains of functions. By definition, you'll see in your textbook and on the Graphing Rational Functions handout, your rational function f of x is really a fraction or ratio of two individual functions. P of x will be the function in the numerator, q of x will be the function in the denominator. So we're going to have an expression with a denominator. Remember, when we were looking at domains of functions, there were two things we had to look out for, division by zero and negative square roots. In this case, we'll really just have to focus on values that will cause division by zero. So when we look at the domain of a rational function, just want to focus on what values will make this function q of x equal to 0. Let's look at example 1 on page 411 of your textbook. So here they give us a function f of x equals x squared minus 9 divided by x minus 3. We really just have to focus on this denominator term. So doing that, even though this is a simpler example, technically if you want, set q of x equal to 0. And in this case, the excluded value will be 3, correct? If we solve this, we'll get x equals 3. Just remember, we need to express the domain in interval notation. So this would be minus infinity 3, u, 3, infinity, just like we did in section 2.6. In part B, they give us another function, g of x equals x divided by x squared minus 9. Again, just like we saw in section 2.6, you really want to take this function and set it equal to 0, find the values that make it equal to 0. Now, as we did in section 2.6, we really just want to factor this expression in the denominator. So the excluded values here will be plus or minus 3. So x cannot equal plus or minus 3. And so again, in our domain notation, that'll be minus infinity to minus 3, u minus 3, 3, u 3, infinity. In part C, they give us one more function to find the domain for. We have x plus 3 divided by x squared plus 9. Now, when we look at this example, if you were to solve x squared plus 9 equals 0, well, we'd get x squared equals minus 9. And technically, if you would solve this, take the square root of each side, eventually you would get x equals plus or minus 3i, which is not a real solution. Right? This is actually an imaginary solution. So in this case, the domain is all real numbers. This example is a little bit different, but it is a good one to look at. And if you really look at the denominator, x squared plus 9, there's no real value of x that you could substitute to make this denominator 0. Even 0, you'll get a value of 9, and any negative will always be squared and become a positive. So again, the domain would be all real numbers. The next topic we'll look at is an important function called the reciprocal function, and we'll just talk about arrow notation briefly. The My Math Lab video you watched on arrow notation covers the topic well, but I'll just recover it with this specific example. So the reciprocal function is 1 over x. Clearly x cannot equal 0, so this would be our domain. There's really one excluded value. And so if you looked at the graph of the reciprocal function, and this is also in the textbook, you would see that we would have a couple segments here and here. Now, there will actually be something we call a vertical asymptote here at x equals 0. That's where we would have division by 0. And we see discontinuities at those points in our graphs of rational functions. So remember, with our arrow notation, this plus symbol means approaching from the right, or the positive x direction. The minus means approaching from the left, or the negative x direction. So as we approach 0 from the right, notice the graph will go up, and it will actually never cross the value of x equals 0 here, and so the function goes to positive infinity. When we approach 0 from the left, we actually get different behavior. f of x will go to minus infinity. So that's why the arrow notation is important. It depends on which direction we're approaching a certain point. And then we can also look at the end behavior of the function. As x goes to positive infinity, this graph will eventually approach 0. The value of the function will approach 0 and approach the x-axis. And it will also do that as we go to minus infinity. And we'll call the line y equals 0. That will actually be a horizontal asymptote. So now let's discuss horizontal and vertical asymptotes. Let's look at the next topic in the chapter, which are vertical asymptotes. And these are really the points where you get division by 0, where you'll see a discontinuity in the graph because the function is undefined there. So, one key characteristic with vertical asymptotes. The graph never crosses a vertical asymptote. That would be division by 0, which is undefined. Rational functions can have none, one, or multiple vertical asymptotes, and this is just an abbreviation I'm going to use. And we can give the vertical asymptote with a particular form of a line equation. It'll be a vertical line of the form x equals a. And the definition is the function increases and decreases without bound around that value of a. Your textbook has a nice illustration of the definition of vertical asymptotes and the general variations you can see. So as we approach these vertical asymptote lines of x equal a, which will be drawn as dashed lines, you'll see that the function will increase or decrease without bound, essentially going to positive or minus infinity, as you approach that asymptote from the right or the left. How do we locate vertical asymptotes? Well, if you have your rational function p of x divided by q of x and it has no common factors, you'll essentially do what we did in example 1 with the domain. Set q of x equal to 0, and the real zeros a that you find in that process, then those vertical lines x equal a will be the vertical asymptotes. Let's look at example 2 on page 415 of your textbook. So this first function they give us, f of x is x divided by x squared minus 9. There are no common factors. And really, we just want to set that denominator equal to 0. And if you factored it, this would be x plus 3, x minus 3. So the roots are plus or minus 3. So x equals plus or minus 3 are your vertical asymptotes. And this is what the graph of that function would look like. Notice carefully, you'll see the dashed lines here at plus or minus 3. And the graph definitely does not cross those asymptotes and increases or decreases without bound on either side of those asymptotes. Let's look at part B. G of x is x plus 3 divided by x squared minus 9. Now it's always important to factor your rational functions, because if you do that, you'll see that here we actually get a factor of x plus 3 that cancels. And so this is a nuance with the graphs of rational functions. Even though in the original denominator minus 3 would cause division by 0, there is a simplified form of the function that all of a sudden that value would not cause division by 0. So this 0 of minus 3 will actually show up as a hole in the graph. And that's what your text is referring to when, if there are no common factors between p of x and q of x, then any zeros you identify from q of x will be vertical asymptotes. In this case, minus 3 is not a vertical asymptote. Only positive 3 is. When you look at the graph of this function, you will see there is our true 1 vertical asymptote of x equals 3, and you see the dashed line, and the function increases and decreases without bound around that value. But notice at minus 3, there you'll see that hole. And again, minus 3 will cause division by 0 in the original function, but in simplified form, it goes away. So this is how it will appear in the graph. In part C, they gave us this function, x plus 3 divided by x squared plus 9, which is actually the same function in part C of example 1 when we looked at the domain. And you might remember that when we solved this and set it equal to 0, we got the imaginary solutions of plus or minus 3i. So in this case, there are no real zeros for our denominator function q of x. So in that case, there will be no vertical asymptote. When we look at the graph of this function, again, we know there are no vertical asymptotes. Clearly, you don't see any asymptotic behavior, and you don't see any asymptotes drawn. So this is the case where we have no vertical asymptotes. Now do pencil problems 3a and 3b. Now let's look at horizontal asymptotes. Unlike vertical asymptotes, where the graph never crosses a vertical asymptote, the graph of a rational function may cross the horizontal asymptote. And Unlike vertical asymptotes, you'll have at most one horizontal asymptote for a rational function. And again, I'm just going to abbreviate it like this, HA. Now, what's our line equation for the horizontal asymptote? Well, for vertical asymptotes, it was x equals a. That's the equation of vertical line. Here we'll have horizontal lines of the form y equals b. And the definition is, for a horizontal asymptote, is that f of x will approach this value b as x increases or decreases without bound. Or you can also think of it as x goes to positive or negative infinity. What's the behavior of the graph? Your textbook will illustrate this definition. So notice, as x, say, goes to positive infinity, it approaches this value y equals b. And we see that here. And even though in this case it does not cross the horizontal asymptote, here we get an example where it does, and then we'll approach that value b as x goes to positive infinity. How do we locate horizontal asymptotes? Well, it depends on the degree of the numerator and denominator functions that make up the rational function. And so n will be the degree of our numerator, m is the degree of the denominator. And depending on those values and how they relate to each other, there are three cases. If n is less than m, the degree of the numerator is less than the denominator, then y equals 0, the x-axis, will be your horizontal asymptote. If those two values are equal, it will be the ratio of the two leading coefficients of the highest order term in the numerator and denominator. And if n is greater than m, the degree of the numerator is greater than the degree of the denominator, there's no horizontal asymptote. Your text will summarize all this information and the three cases we just discussed on page 417. Let's look at example 3 on page 417 of the text. So in part A, they give us f of x equals 4x divided by 2x squared plus 1. So the highest order term here is x. That has a degree of 1, so n is 1. Here our highest order term is 2, so m is 2. And that's case 1, where n is less than m. So our horizontal asymptote will be the x-axis, or the line y equals 0. This is the picture of the graph you'll see in your textbook. And notice, as x goes to positive infinity and negative infinity, the graph will eventually approach that horizontal asymptote of y equals 0. In part B, they now give us g of x is 4x squared over 2x squared plus 1. So all they've really done is take this function and square the numerator term. Now the degree of the numerator is 2, that's our highest order term, and the degree of the denominator is still 2, just like in part A. But now, because n equals m, that is now case 2. So now our horizontal asymptote will be the ratio of the leading coefficients of those highest order terms. So this is a sub n, and this is b sub n. So y equals the ratio of those two coefficients. So it'll be 4 divided by 2, or y equals 2 is the horizontal asymptote. This is the picture of the graph of that function, and you can clearly see as x goes to positive and minus infinity, the graph will definitely approach that horizontal asymptote of y equals 2. In part C, now h of x is 4x cubed divided by 2x squared plus 1. So now the degree of the numerator is 3, n equals 3, and m equals 2. This is now case 3, where n is greater than m. And in this case, there will be no horizontal asymptote. When we look at the graph of this function, you can clearly see that as x goes to positive infinity or minus infinity, the function is going to increase without bound. There is no horizontal asymptote. Now, do pencil problems 4a and 4b.